Thank you, everyone. Hello. Thank you for your interest in Easy5 and for attending today. As Eugen said, I'll start off for the benefit of those who may not know anything about Easy5. I'll give a brief overview, and then I will talk about the new features in Easy5 2017. Easy5 is a set of software tools for system-level modeling, simulation, and analysis in which physical equations, which constitute the mathematical model, are encapsulated by components which are represented by icons. Each of the icons represents a mathematical model for a subsystem or a component. By connecting the components together with the connection lines, we establish data flows between the components, and in this way create a system-level model. Inputs to an Easy5 model can include design dimensions, different types of parameters that are intrinsic to a component, the connectivity between the components, the types of analysis which you are interested in, and the output that you request. The output from an Easy5 analysis depends on what type of system you're modeling and what type of analysis is being performed. For a typical transient simulation, you would get lots of time-varying system responses such as pressures, temperatures, flows, displacements of poppets or actuator cylinders, that sort of thing. Velocities, heat transfer. If it's an electrical system model, then the output would be voltage and or current, electrical performance. Easy5 development began in 1975 with Boeing, and in 1986 became a commercial product with a graphical user interface. In 2002, it was purchased from Boeing by MSC Software. So active development is in continuous from power generation, refrigeration, and cryogenic systems, a number of different types of systems that can be modeled in Easy5. And the models can be multidisciplinary. For instance, you can have a model that has both electrical systems components and hydraulics library components, and interconnect the two different disciplines in a physically meaningful way. Easy5 components can be very low-level mathematical blocks. In this particular example, in the lower right-hand corner, each Easy5 component represents a specific mathematical operation such as multiplication, division, or integration. And in this way, if you know the equations that need to be modeled, you can build up a fundamental engineering model of something like a spring mass damper system. There are a number of commercial application libraries available, or many users develop their own application libraries for high-level modeling in Easy5. And this means that the end user doesn't necessarily know the equations in detail. Those are built into the library components. And then the end user just needs to know physically realistic design parameters and initial conditions to create a physically realistic model. In the example on the bottom, we have a hydraulic actuator connected both mathematically in the physical world and schematically in the Easy5 model to a mechanical rack and pinion. By populating the component data tables with physically realistic design parameters and initial conditions, one can create a system-level model of this type of a system. Easy5 users can also create their custom blocks, their own custom blocks using Fortran or C code, defining inputs and outputs for the component. And they can customize their icon for the component. There are a number of commercial application libraries which are available for Easy5. MSC supplies a thermal hydraulics library, which we'll be discussing further in the presentation. Also, a gas dynamics and pneumatics library, a multi-phase fluid library for modeling refrigeration and cryogenics, an aerospace vehicle library for modeling airplane control surfaces and airplane flight, and an electrical system library for modeling electrical power systems. Ricardo supplies some commercial application libraries as well, a powertrain library, fuel cell library, and an engine library for modeling automotive systems. Easy5 users can create their own libraries for in-house encapsulation of knowledge and for reuse within their companies, using the same techniques that we use in reading the commercial libraries. For instance, GE uses a number of different custom libraries in their facilities throughout the world for modeling the systems that they're interested in. Easy5 comes with a number of interfaces to other software tools, notably MATLAB Simulink, Atoms, and in the illustration here, the Atoms model includes FEA. And then something that we'll be talking about further today is the interface between Easy5 and functional mockup interface. So that's a quick overview of Easy5. Now we'll go to the new features. Okay, the first new feature is global and submodel configuration parameters. Now, what does that mean? First, let's talk about what is a configuration parameter, what is a dimension parameter. These have always been part of Easy5 at the component level. Configuration parameters have been part of Easy5 at the component level since about 2004. And dimension parameters have been part of Easy5 from the very beginning. With a configuration parameter, you can select from a pull-down list between different component formulations that provide different features. For instance, in this example, the second configuration choice here is a heat transfer formulation, which allows the user to select between externally supplying a heat transfer coefficient or having the component internally calculate that heat transfer coefficient. As an example of a dimension parameter in the gas dynamics library components, one specifies for variable composition systems the number of gas species in the system. And in the past, that has had to be specified on a component-by-component basis. Global configuration parameters and submodel configuration parameters allow the specification of these type of dimension parameters or configuration parameters that can be set on a model level basis or on a submodel level basis. So one of the examples illustrated in this slide is that number of gas species, which on the previous slide was set on a component level basis. Now, in a future release of the gas dynamics library, we'll be able to specify that on a model level basis or a submodel level basis, which will be both more convenient for the end user and more reliable, less prone to error. Another application for these global configuration parameters is to allow the hydraulics library user to choose between different levels of model fidelity. Historically, and by default, it continues to be this way, hydraulics library models are high-fidelity models. The library developers strive for as high a fidelity as possible, consistent with a reasonable performance. And this results in models which are numerically stiff and which contain events. So the integrator that's used has to be a variable step integrator, and it needs to be able to handle state-related events. The hydraulics library now has another level of fidelity included with it, which we call reduced order. The mathematicals for the components, when they are reduced order, are not numerically stiff and do not contain state-related events. This means that they can be, these models at the reduced order can be integrated with an explicit Euler integrator, and that is necessary for the support of real-time hardware and unit simulations. Todd will be giving a demonstration of this later. Another hydraulics library enhancement in Easy5 2017 is some new options for discretized pipes. For the transient momentum lumped parameter pipe PD, there is now an option for temperature discretization. This pipe has always included flow discretization and pressure discretization. Now there's optional temperature discretization for that as well. For the steady momentum pipe PI and the steady momentum hose HO, there's now an option for pressure and temperature discretization. This allows the user to model a temperature profile within a single pipe component. Okay, moving away from the hydraulics library for a little while, another new feature in Easy5 2017 is support for functional mock-up interface, or FMI, for model exchange. Functional mock-up interface is an open standard which allows the creation of multidisciplinary, multi-vendor simulations. In this example that's illustrated, we have 5 different functional mock-up units, or FMUs, modeling an engine, a gearbox, the thermal system, some mechanical systems. And these are all coupled together into a system-level simulation using the functional mock-up interface standard. If you've never heard of FMI before or need to learn more, the starting point for that is the fmi-standard.org. Now, Easy5 2015 introduced support for FMI for co-simulation. For co-simulation, the functional mock-up units include the solver that is specific for that product. So if you export a co-simulation FMU from Easy5, that's going to include all the Easy5 solvers. FMI for model exchange means that the FMU does not include a solver. The FMU supplies state derivatives, and the solver supplies the state values and the time. So it's up to the FMI master to be able to integrate the FMU that's exported from Easy5. Now, going back to the hydraulics library for just a minute, if you have an FMU that's exported from a model that is reduced order, then it's highly likely that just about any FMI master will be able to integrate that FMU. two aspects of FMI support in Easy5. One is FMU export. The external modeling interface library, which is the same library which is employed to export MATLAB Simulink S functions from Easy5 or to do other types of exports. That's provided to export both model exchange FMUs as well as the existing post-simulation FMUs. And then the integrated simulations can be run in other tools using the Easy5 generated FMU. For model exchange export from Easy5, only the FMI version 2 standard is supported. Also included is FMU import into Easy5. In Easy5 2015, we introduced an extension component that could import post-simulation FMUs into an Easy5 model. And so FMUs exported from other vendors could be imported into Easy5 models using this method. And then the Easy5 model could act as the FMI master. For Easy5 2017, this extension component has been extended to include model exchange FMUs, and both the FMI version 1 and FMI version 2 standards are supported for both model exchange and post-simulation FMU import into Easy5. Okay, my last slide. Where do you find the documentation for this stuff? A good place to start is the Easy5 2017 release notes and the new features examples, which can be downloaded from the same site from which you download the installers for Easy5. Now, besides those two places, the new hydraulics library features are documented in the component data tables for those components. Global library configurations are documented in Chapter 12 of the Easy5 User Guide. That's the chapter on library development. FMU export is documented in the External Modeling Interface Library User Guide. FMU import is documented in the extension component info page. And I am done.
Okay, I'm going to pass the presenter to Claude. Hi, Claude. You can go ahead and share your screen. Yes, we can see your blue screen right now.
Okay. Hang on a second.
Yep, we can see the Easy5.
Okay. All right. Okay, can everybody hear me?
Yes, but I cannot see Easy5 on your screen now.
Okay, hang on. Let me get rid of this. How's that?
I think you're sharing the wrong, not the correct monitor. Still no Easy5.
Says monitor 1. Let's see. I'll move it to monitor 2. Try that.
Yes, I can see it. Yep.
You see Easy5?
Yes, we can.
Okay, so it just reversed monitors on me. Okay, hello everybody, and I will just demonstrate one of the features that Dan was just talking about, and that is reduced order modeling, but this will also show how you use global configuration parameters. So here I have, and I'll just make this a little bigger. Here I have a model that those of you who use Easy5 will be pretty familiar with. This is a just a simple actuator positioning system and a servo actuator, and we've got a actuator here, a servo valve here, and a sort of a constant power hydraulic power supply here, and a control system, simple PI control system. So this is modeled using the hydraulics library, and we can run a simulation of this. I'm going to build the model now, and then I'm just going to run a simulation, and we can take a look at the plots here. So here you see as it runs, the commanded position is in blue, and the response is in black. So it's kind of what you expect. I'm going to zoom in a little bit on the response up here. So you see the response is pretty well damped and comes up right to the command there. So this is modeled with the high fidelity hydraulics library that we have. And so if you take a look, as Dan was talking about before with configurations, for instance, if I look at this actuator, there are a number of inputs here. There are a number of secondary inputs to the actuator. And if I look at the configurations, I have all of these configurations. I can change its mass dynamics. I can add snubbers to it, all sorts of stuff, and add numbers of inputs and outputs. Okay, and this is what's called these are configuration parameters that the library developer sets these up so that they can configure, when you execute the model, the performance of the actuator, how it actually responds. So what we've done is use global configuration parameters to actually change how the components are actually configured in a global sense. And when we do that, we can, in this example, we can reduce the order of or reduce the fidelity of the simulation in order to be able to speed it up to run in hardware-in-the-loop simulations. And we're going to sacrifice some fidelity for getting much faster compute speed so we can get it inside the time frame of our hardware simulator. Okay, so how do we do this? Well, it's pretty simple the way it's set up. I just go to the options menu here. I go to set model global configurations, and here's our hydraulics library. And I see that there's a parameter reduced order modeling. And right now it's set to full fidelity. So I'm going to set it to reduced order there and say OK. And you notice I put this special component in here. It just, all this does is notify you that this model is now set to reduced fidelity. And if I take a look at this actuator again, you might remember that there were a few more configurations here that were available that are no longer available. So the configuration of this actuator has actually changed, and the mass dynamics inputs have actually changed. What we're going to do is approximate some of the hard limits instead of using switch states. Easy5 uses switch states normally in the hydraulics library, for one thing, to model hard limits. But switch states are problematic for fixed step integrators and problematic for FMI at this point. So not so much for FMI the way we do it, but actually for other integrators outside of Easy5 that might try to use them. So what we want to do is avoid switch states. So we don't have any switch states. They're gone. All right, so let's try a simulation here. I'm going to rename the simulation to reduced order. And I'm just going to run the simulation. Well, actually, I'm going to change this. Let's run it with BCS gear first, which is our normal our normal integrator, variable step integrator. It's going to compile again, and now it's going to run the analysis, and it's run the analysis again, and here are the results. And you'll notice there's a little bit of an overshoot there. That's because the dynamics, the fidelity of the dynamics at the hard limits has been reduced. There's now a kind of a stiff spring there instead of an actual hard limit. So, but that allows us to simulate using a fixed step integrator much more easily. So I didn't use a fixed step integrator here, so let's try a fixed step integrator. And in fact, okay, let's try that. Here I'm going to change this to Euler, and I'm going to put in another, decrease the time step by 10 because Euler may go unstable at that higher time step. So let's try this again. Okay, let's see what we look like here. Yeah, still have the overshoot. Now we can take a look at what we originally had and compare that to what we're looking at now. And you can see here the difference in response. Here's the actual hard limit model, the black line, and here is our response using fixed step Euler integrator with a 1 millisecond time step and a reduced order. And here, this is fairly, you can see, looking at the gross level, the response looks pretty good. I mean, it's almost the same. So you might think, okay, well, I can get away with this reduction in fidelity. And that might be the case. We can take a look at the pressures, though. The pressures, though, are quite different at certain places. So it depends on, here, to take a better look at that. So you can see these pressures here are quite different. So it depends on your judgment as an engineer whether this is a good enough approximation or not. So, but what this does allow you to do is, if you can live with these slight differences, or maybe not slight differences in pressure, depending on your view, but you can live with those pressure differences and use this overall response as adequate, then you can actually speed your simulations up quite a bit, enough that you can get inside of a 1 millisecond time frame easily and run this in a hardware simulator. Using an FMI, you can export this model as an FMU and run it in another simulation program, or you can run it with any hardware simulator that interfaces with FMU's FMI, like DSpace. I think that's about all I have to show, unless there are some questions.